You may have heard about bioremediation. This is a process where bacteria break down contamination in an area. Bioremediation is often used to clean up underground oil contamination, for example, from leaky underground storage tanks or from surface spills that seeped into the groundwater. Bioremediation can also be used to treat acid mine drainage. Microorganisms like bacteria perform chemical reactions, and the ones used by sulfate-reducing bacteria that degrade acid mine drainage look like this. In this chemical equation, CH2O is commonly used to describe organic matter. So we see organic matter, sulfate, and protons are reactants, and hydrogen sulfide and bicarbonate are products that form. The H2S that forms can then react with metals in the water, or Me, in this reaction. H2S and Me2+ are both the reactants, while MES and or metal sulfides and H+ are going to be the products. You can see that these two reactions consume sulfate and aqueous metals, both very important for treating acid mine drainage. Both of these reactions have arrows that point towards the right, meaning they are irreversible. Thus, when conditions are favorable, the reactants will react to form the products. These two irreversible reactions are also related to a reaction that describes the concentration of protons, or H+, in the water. So that's here. So you can see on the left side we have H+ and OH-, and then on the right side we've got H2O. This reaction has a double arrow, indicating that it's irreversible. Thus, in water, H+ and OH are combining to form H2O, and H2O is decomposing to form H+ and OH-. If the reaction rates of both of these reactions are equal, the concentrations of H+, OH-, and H2O are not changing, and the system is said to be at equilibrium. These are some examples of chemical reactions that are important to environmental engineers. In this video, I want to give you an overview of all of the types of chemical reactions you may encounter when analyzing environmental systems, or at least most of them. By the end of this video, you should be able to define the following: irreversible reaction, reversible reaction, limiting reactant, and reaction rates and reaction rate orders. Let's start with irreversible reactions, like the one I described using sulfate-reducing bacteria to break down components of acid mine drainage. Irreversible reactions may be stoichiometric or non-stoichiometric. Stoichiometric reactions are ideal, meaning exactly the correct amount of each reactant is present at the start, and none of the reactants are present at the end of the reaction. Let's look at this equation. This reaction would be stoichiometric if 1 mole of H2S was present for every mole of Me2+. At the end of the reaction, no H2S or Me2+ would remain if it is stoichiometric. A non-stoichiometric reaction has a limiting reaction that is used up before the other reactants. In this chemical equation, if we had 1 mole of H2S and 2 moles of Me2+, then H2S would be the limiting reactant, as it would be used up before Me2+. The amount of H2S present would dictate how many products formed, and Me2+ would remain in solution after the reaction goes to completion. The seeming opposite of an irreversible reaction is a reversible reaction. Reversible reactions proceed in the forward and backwards direction simultaneously. A very common reversible reaction is the one we talked about earlier, where H+ and OH- are interacting with H2O. So at equilibrium, both reactants and products will be present and their concentration will not change. However, the reaction is still going on, It's just that the forward reaction is balanced by the reverse reaction. For equilibrium reactions, you can look up equilibrium constants to determine the relative concentration of reactants and products. Let's examine the generic chemical reaction. So here we have A and B combining to form C and D. The lowercase letters are the stoichiometric coefficients. You've probably seen this type of notation in your chemistry class. In this reaction, the equilibrium constant, or KEQ, will equal the following. We have C raised to C, D raised to small d, divided by A raised to small a, and B raised to small b. So in these types of problems, if you're given the concentration of reactants, you can use the chemical equilibrium constant to calculate the concentrations of products and vice versa. While equilibrium constant is a generic term that can be applied to a multitude of situations, these constants have specialized names when they're used in specific different situations. For example, Henry's law describes equilibrium between a gas in the vapor phase and a gas in dissolved water. So here we have some chemical A in equilibrium between the gas and the aqueous phase. So we can define Henry's law constant, which is just an equilibrium constant, but for a specialized situation, as the molar concentration of A in the aqueous phase divided by the partial pressure dissolved in water, or the partial pressure of the gas. Whenever you use Henry's law, remember to use the molar concentration of A in water with the partial pressure of A in the vapor phase. Another type of equilibrium constant is an acid dissociation constant. These are constants that describe chemical equilibrium between acids and their conjugate bases. For example, in the following equation, HB is a generic acid and B negative or B minus is a conjugate base. So we have HB dissociating into H plus and B minus. Acid dissociation constants are normally written as Ka, and this one would be the product of H plus and B minus divided by the concentration of HB. So remember to always use molar concentrations whenever you're doing these equilibrium equations. So whenever you're dealing with chemical equations, be sure that they're always balanced, and remember to use stoichiometric coefficients to relate molar and not mass concentrations of the reactants and the products. You may use irreversible reactions to calculate the amounts of reactants or products when reactions go to completion. You may also use equilibrium constants to calculate concentrations of species that are in chemical equilibrium, that is, reversible reactions. However, there might be some situations where you're interested in the rate at which an irreversible reaction occurs. These are reaction rates, and they can be used to describe the speed at which irreversible reactions occur. For example, reaction rates can be used to calculate concentrations in effluents from treatment processes, or the time it's going to take for a process like bioremediation to clean up a site to an appropriate level. Reaction rates are described using reaction rate orders. While these can often be assumed from stoichiometry, and you probably saw this in a chemistry class, they must be determined experimentally. Most common in environmental engineering situations are going to be first order and pseudo first order reactions. So here is a first order reaction where A is going to be in C, and you can see that the stoichiometric coefficient of A is going to be 1. And so this indicates that it might be a first order reaction, and we can write the first order reaction rate here. So we have a negative on the rate because A is disappearing. K is the reaction rate constant, and then multiplied by the molar concentration of A. Pseudo first order reactions can be treated like first order reactions in calculations that involve reaction rates, and thus they're very popular with engineers. However, the pseudo first order reaction rate might depend on other variables. So here is an example of a pseudo first order reaction rate R. Again, in this situation, the reaction is consuming A, so the reaction rate is negative. K is the reaction rate constant. The prime is used on pseudo first order reaction rate constants multiplied by the molar concentration of A. You can use reaction rates when incorporating chemical reactions like generation or consumption into mass balance equations. So this concludes my whirlwind overview of chemical reactions in the environment. Now I want you to be able to define the following: irreversible reaction, reversible reaction, limiting reactant, reaction rate, and reaction rate orders. In coming videos, I will go into more detail on how to apply each of these types of reactions to environmental systems analysis.